Welcome to Summarize Science. Today, we're diving into a cosmic event so powerful it shakes the very fabric of space-time, the dynamical capture of black holes. What happens when two black holes, not bound by orbit, have a close call? Sometimes, they don't just fly by, they get trapped in a gravitational dance that ends in a cataclysmic merger. In this paper, researchers used powerful supercomputers to simulate this exact scenario. As you can see in this diagram, they sent two equal mass, non-spinning black holes towards each other. They tweaked two key things in each simulation, their initial speed and their angle of approach. This allowed them to study a whole range of close encounters and their outcomes. Each of these events creates ripples in space-time called gravitational waves, and the simulations showed that these captures produce a unique, two-part signal. First, there's a burst of waves from the initial close encounter that captures the black holes. Then, after a brief, temporary orbit, there's a second, more powerful burst from the final merger. The scientists even created a simple mathematical model that accurately describes this gravitational wave song. One of the most fascinating findings is the identification of a precise tipping point. There's a critical angle of approach that separates a capture from a simple flyby or a scattering event. As the simulations got closer and closer to this critical angle, the time between the first and second gravitational wave burst shot up towards infinity. This is because at that exact angle, the black holes would theoretically orbit each other forever without merging. It represents the ultimate cosmic balancing act. So what about the new, single black hole created after the merger? Its properties, like its final spin and mass, depend heavily on that initial encounter. Interestingly, the relationship isn't simple. As the angle of approach changes, the final black hole's spin first decreases, hits a minimum, and then starts increasing again. The researchers also found that these mergers radiate away a huge amount of mass as energy, between 3 to 6% of their total initial mass. So, to recap, researchers have modeled the unique two-part gravitational wave signal from black hole captures. They've pinpointed the critical angle that separates a capture from a near miss. And they've shown how the final, merged black hole's properties depend on these initial conditions in complex ways. This work is crucial because it provides a blueprint for what scientists should look for in real data from detectors like LIGO. By understanding these signatures, they might soon be able to identify these incredible dynamical captures happening in the most crowded corners of our universe. Thanks for watching Summarize Science.